Well, let's look at what happens when we have two different aldehydes, and I'm going to draw them generically, making sure that I show that they have an alpha hydrogen or two, just with two different R groups, and we're going to call this a crossed aldol. So what happens in this case when we react these with NaOH, and we're not going to worry about the condensation product, we're just going to draw these as the addition product. So we're going to use the first molecule as the nucleophile. That would be one possible product. The first molecule could also react with itself. So there's both R groups are the same in this case. The second molecule could be the nucleophile. And it might react with the other molecule. The second molecule could react with itself. And of course, if we added some heat, we could get some elimination products, we could get some condensation products. But you see the problem here, right? We're going to get 4 different products. And that's generally undesirable. So most of the time, chemists do not take random aldehydes and mix them with other random aldehydes and expect to get a useful product out of it. So how do we prevent this? There are a couple ways, techniques we can use to prevent this crossed aldol 4 different product outcome from happening. First way we can do this is use a compound with no alpha hydrogens. That can at least cut down on some of our outcomes. So let's look at this possible aldehyde with a T-butyl group on one side, aldehyde on the other, and we'll react that with acetone. Acetone is obviously going to be the nucleophile, so we'd form the beta alcohol right there, T-butyl group on the other side. There are no alpha hydrogens here. And the aldehyde is a better electrophile than the ketone. So we don't have too much concern about the ketone reacting with itself to make a homo-aldol product. So basically we have the nucleophile is really only going to react with this electrophile, giving us just one outcome. You could also use benzaldehyde or other forms of aromatic aldehydes. We saw one in lab, I think last semester. We're going to see it again this semester, vanillin. So any of these would be great electrophiles for use in an aldol condensation. Another option would be to use a strong base to irreversibly produce the enolate, then react it with the electrophile. So what if we did this? LDA, lithium diisopropyl amide, remember that's the really strong base. It is an irreversible reaction. We're going to form this anion, which we can then react with, let's just say, a smaller aldehyde. This is the nucleophile. Since we've formed 100% deprotonation at this position, we formed 100% nucleophile. None of this is left to react as the electrophile. We add then the electrophile next, and we can make the desired product in high yield. Right, so that's what be the desired product. We're making this bond right here between this nucleophilic carbon and the aldehyde carbon. And so this might be called a directed aldehyde. I'm sorry, directed aldol. And this product gets produced in good to high yield instead of, like you saw on the previous slide, the crossed aldol, where we had 4 potential products that were probably produced in very equal yields. All right, before we end, let's get a little bit of practice with some predict the products, or in this case, I think we're going to produce something via the aldol. So let's look at this product. I want a phenyl ring there, not an R. So the goal might be produce this product via the Aldol reaction. And I'll give you another one to work on. You can pause the video, think about it for a few minutes, then come back. So produce these via the Aldol reaction, via a condensation or an addition. If we examine the first structure, we have a beta alcohol next to our carbonyl. And so that's your clue as to where the bond is that's going to be formed in the aldol. It's always going to be this bond right next to the beta alcohol on the alpha carbon of the carbonyl. So this bond is formed. So we need two pieces, one of which is inside that dashed line, the other is outside the dashed line. So I would say this ketone would probably react with, I'm going to draw the ring here, that aldehyde. Can you see how this blue aldehyde that I drew is coming, or produces what's inside the dashed blue line here after I attack the aldehyde and push electrons onto the O? So we deprotonate at one of these positions, we attack the carbonyl of the aldehyde, the carbonyl carbon of the aldehyde, we create an alcohol from the aldehyde. And so it's this bond that's being produced in this reaction. Let's look at this other option. In this case, we see that there's some unsaturation. So we call this an alpha-beta unsaturated complex. In this case, it's a ketone. And what we can do here is simply cleave that double bond. So that double bond comes from the one of the ketones we started with, one of the carbonyls we started with, and you can see how this alpha carbon here probably just needs two hydrogens in order to go back to the standard starting material. So that's probably our nucleophile, and that's going to be our electrophile in this reaction. We deprotonate this H, attack the aldehyde, run the condensation mechanism, and we form the double bond here. Another way to look at this is to recognize that this alpha position actually lost two hydrogens. So if I were to sort of grab these two, grab this one, right? You redraw the carbonyl without those hydrogens. You can't tell that they're missing, but redraw the aldehyde without the oxygen. You can see how it would be easy to replace those two hydrogens with a double bond to the what used to be the carbonyl carbon. So that's how we might deconstruct both the aldol addition products and the aldol condensation products. One last thing I want to show you is an intramolecular aldol. And that allows us to make ring structures that have functional groups present. So functional groups on the ring. So let's look at this example. If we heat this, we're actually going to get an unsaturated ring system. So we can use, first I'm going to number these carbons so we can keep track of them. That's probably one of the most important things to do in this case. Again, it's very easy to lose track of carbons. I showed you a few examples of myself doing that over these past few minutes. So what we're going to do then is deprotonate at one of these alpha carbons, either 1 or 6, use that to attack the carbonyl on the other side of the molecule. So we're going to make a 5-membered ring. If I make a bond between 1 and 5, I've made a 5-membered ring. So I'm going to start by drawing that 5-membered ring. That's the first thing I'm going to do when faced with this question. How large is the ring going to be? And then I'm going to number the carbons. It really doesn't matter which way I number, so let me just choose a random numbering. I know how it'll look nicely, but I just want to show you what happens if we choose a random number. Now we are missing carbon number 6. Where is carbon number 6? It should be attached to carbon number 5. So let me draw carbon number 6 and then label it. And I'm missing a few other things, right? Carbon 2 should have an unreacted ketone. And carbon 5 should have, I think that's going to have the alcohol that we form in the aldol addition. So that's going to be the new aldol addition product. If we involve some heat, we're going to further remove a beta hydrogen from carbon number 1 to make that molecule. And I'm going to redraw that in the way I would draw it so it looks a little nicer. Again, it doesn't matter which way you do it. Let's number these carbons again. And this one would be 2, that would be 1. So you can keep track of those. So you'll notice that we made a bond between 1 and 5, and we can predict, we could have predicted that earlier because we know 5 had the carbonyl. The carbonyl carbon is one of the ones that participates in the newly formed alkene, along with whatever alpha carbon we're using to deprotonate. And you can see that we couldn't have used 3 or 4 to attack the other ketone because that would have made a 3-membered ring if I tried to use 3 as the nucleophile, so that's just not going to work. It's going to be too strained. So we're going to use 1 to attack 5 to make a 5-membered ring. We're going to create our double bond between 1 and 5 because we know that we're doing an aldol condensation because we have heat involved here. So we can predict a double bond between 1 and 5. Once I draw the ring, I just have to number it, add the other substituents as you saw me do, and then I have this product. And so again, I've got the alpha, beta, unsaturated ketone, which, as we'll see later this chapter, can be used in other types of reactions. We could also use this in a Diels-Alder reaction. This is a great dienophile.